Hello everyone, my name is Morokot Sakal. I am a PhD student in the Space Vehicle and Robotic Lab at Florida Tech. And today I would like to talk about an adaptive attitude controller that uses a radial basis function neural network to learn the reaction wheel held online. So here is the roadmap of my talk. First, I will start with the motivation, then the problem statement and our objective. Then I will explain the controller design. Then I show the simulation result. And finally, I will finish with key takeaway and future work. So I would like to start with some context. So reaction wheel array is a commonly used in small satellite because it provides a precise attitude control. However, we know that the reaction wheel itself is degraded over time due to heat cycle, radiation, some other environmental condition. So we would like to design a controller that still allow us to maintain a precise attitude control even when the wheel is degraded or failed. So we design an adaptive controller to address this issue, which I will talk about in more detail in the next slide. So this slide shows the overview of the controller that we designed last time. It's called the integral concurrent learning based controller. And in this problem, we are assuming that one of the wheel is degraded, as you can see in this plot, and the controller doesn't know about it. And what it does is that as a satellite maneuver, the controller have an adaptation law that you can see in this flow block that collect input and output data as a satellite maneuver, and it ensure that this estimated health can be converged to the true health, as you can see in this plot. However, we made one assumption with this controller is that we are assuming that this health is constant or slowly varying, which is not the case in reality. So we want to lift the assumption by proposing using a neural network to model this nonlinear health of reaction wheel. So that is the motivation of this talk. So we still want to have a controller that still be able to maintain attitude tracking, but this time the controller will be able to learn a nonlinear time-varying wheel health by applying the radial basis function neural network and concurrent learning based adaptation law. So what we're doing is that we embedded this RBFNN into this adaptation law and make some change to our controller. So first, for the health model, we allow the health to be changed non-linearly instead of having just constant. And instead of directly estimate this health factor, now we will estimate the RBFNN, weight, and bias. So now let's start with some problem statements. So I will first start with attitude dynamics model. So the model is consists of Euler equation plus the kinetic equation. And what I want to emphasize is this actuation term that you see on this right side that is depend on phi, which is the uncertain actuator health matrix. And what we want to do here is we want to rearrange this term to have the following expression where we bring the wheel health of the wheel to the right side, as you can see here, because that is required by the adaptation law. And the next step is how we want to approximate this wheel health using RBFNN. So this slide shows how we model the RBFNN. How we model the health of the reaction wheel using RBFNN. First, I would like to explain why we want to use RBFNN. It's because it allows us to have a linear envelope as long as we assuming that the center and the width of the RBFNN is fixed. And in this problem, we are also assuming that each wheel are independent to each other. It means that if one wheel fails, it's not going to affect the other wheel. So we assign one RBFNN network for each wheel. With that, now we can express this 5x to have its own RBFNN network, as you can see in this plot. So now for each wheel, its output is now depend on the weight of the RBFNN. With input, it can be temperature, it can be in other thing, plus some approximation error. And in this slide, what we going to do here is also again doing some manipulation. And what we get at the end is this expression where we also want to bring the unknown term, in this case, the weight of the RBFNN, to the right side. The similar thing that we did with 5.8. Okay. So now I want to talk about the control objective. So here we first define the error MOP sigma E that represent the mismatch between the satellite and desired altitude trajectory. And then we define the relative angular velocity, omega alpha, that is also depend on the rotation matrix between the satellite and desired trajectory, which is all tilde. And now we can form this kinetic equation. And we can formulate our objective as that the control objective will be achieved is we be able to show that sigma error will go to 0. That is equal. This also mean that the relative angular velocity will also go to 0. And it also mean that sigma E dot will also go to 0. And which imply that this rotation matrix will go to identity as the time go to infinity. So now let's talk about control development. So first, to develop a controller, we first introduce some modified state vector R that is depend on sigma dot E plus alpha sigma E. And we can take the time derivative of that to get this expression of R dot that have the following expression. And this will depend on omega dot. And we can get this omega dot from the Euler equation of motion. And here we can obtain the open loop error system or dot that have the following expression. And now it's depend on the weight of the RBFNN. And here I also define the W hat is equal to the estimation of the weight, and W tilde is equal to the estimation error of the weight. And now we can propose the controller UD that have the following expression. And then by this, we can set phi W hat to equal to this controller. And now we can obtain the apply control torque to reaction wheel with the following expression that is depend on the Hell, the estimated Hell of the wheel. And how do we get the estimated Hell? It's actually depend on this expression. That's also depend on the estimated weight of the RBFNN. So as long as we can estimate the weight of the RBFNN, now we can estimate the Hell of the wheel. So to do that, this slide show how the controller be able to update the weight in real time. So we have this expression that is W hat dot. It's not W hat. We mean that we need to integrate this. And this term is called adaptation law that depend on two terms, the gradient term and the concurrent learning term. The gradient term will depend on the current error, and the concurrent learning term have this term that collect the input output the data online. So the way it works is that the controller will first start it maneuver and start collecting data. And first we don't enable this concurrent learning term yet. We wait until this finite excitation condition has been met. That's defined here and also user defined. Once this condition has been met, the controller will enable this concurrent learning term, which enable the controller to drive this weight to the true value, which means that the weight will converge and mean that we can estimate the real health. In this paper, we also discuss how the stability of controller become, but due to time constraint, I will not talk about that in detail, but this is the overview of that. So depend on when the final condition has been satisfied. Before that, we ensure that the tracking error will be bound using this following expression. But after time t, when the final condition has been satisfied, we also be able to show that the weight error also converge exponentially. So now let's talk about the simulation. First, I need to set up the model for the true health of the reaction wheel. And the way it works is that we make the wheel head to to be depend on the temperature of the wheel that is have the following expression. And the temperature of the wheel is now depend on how much torque you apply and how much it's spinning. The more you spin, the more it will heat up. And if you don't not using the wheel, it will cool down based on the temperature of the environment. And this is an example of what it looked like. This plot here show the temperature profile when you use the wheel, and that corresponds then to the change in the wheel profile health that is degraded as the temperature rising. And now we can set up the RBFNN. And in this case, we are assuming that the input of the RBFNN will be the winding temperature of the wheel. And for each of the wheel, we have set up 10 RBF plus 1 bias because we have 44 wheels that result in 44 unknown parameters to be learned by the controller. And for the test scenario, we are assuming that the wheel number 4 will be degraded, and we run this simulation for 10 hours. And during that time, the controller will switch its guidance between inertial and nadir every 12 minutes. And these are the simulation parameters. So now I would like to talk about the result. So first, these two plots in the left show the attitude error and angular velocity, body angular velocity of the spacecraft. And because of the long simulation, what you see here is just a long, many spikes, but these spikes actually correspond to the guidance switch that happen every 12 minutes. And you can see that when we zoom in this plot, it's confirmed that the tracking error of this controller is converging as expected. And due to this maneuver throughout the time, because we have one wheel is degraded, it also caused some change in temperature, as you can see in this plot. And that also corresponds to this nonlinear change in the true health of the reaction wheel. The rest of this plot is related to the plot for the estimation part. For sigma, for plot E is actually the plot of the finite excitation condition matrix lambda. And then we have the estimated health here. And lastly, the plot of the RBFNN weight and bias. So we can observe in this plot that before the FE condition has been met, the estimated health of the wheel is wandering around 1. It's not be able to track the true health of the wheel. But after time t, when the condition have been met, now the controller be able to correctly estimate the true health of the wheel. As you can see that it closely track the true health of the wheel. At the same time, we also can see that the RBFNN weight and bias is also converging. I also want to show one additional thing that we observe from the simulation is that we run the exact simulation, but having two cases where we disable the CL and also enable the CL. So you can see here when we disable the CL term, the controller was not be able to closely track the wheel health. The true wheel health of reaction wheel number 4, it means that it continue to apply torque to the wheel. It result in the wheel number 4 is degraded to be overheating. But if we enable CL term, it be able to track the wheel properly, health properly. So it will help prevent the wheel number 4 temperature from also rising. So in conclusion, in this study, we design an adaptive controller using RBFNN and concurrent learning adaptation law. And we show that the controller be able to maintain attitude tracking and be able to learn the wheel health when the wheel health is nonlinear and time varying. We have integrated this RBFNN into the controller, but still show that it retain its stability guarantee. And in simulation, we also be able to show that the wheel able to allocate the torque correctly, therefore help preventing the degraded wheel from overheating. In the future work, we want to improve the wheel health model by using on-orbit temperature data, and we also to further validate the controller on the hardware-in-the-loop testbed, and also explore other complex neural network architecture to improve the controller further. And thank you so much for your attention. If you have any question, you can reach me out in this following email. Thank you very much.